On September 14th, the interstellar comet known as Tri-I/Atlas shattered all forecasts, exploding with brightness and revealing a ghostly green shell 500,000 kilometers wide, containing 8 times more carbon dioxide than water. Her sudden outburst left even experienced astronomers bewildered, as forums and official channels filled with messages of confusion and alarm. At this moment, Tri-I/Atlas accelerates toward a close pass by Mars, leaving behind an anti-tail directed toward the Sun, while most major observatories stand still in anticipation. The closer the comet approaches Mars, the more terrifying it becomes. What caused this cosmic deviation, and why are critical data disappearing just as the mystery deepens? The answers cast doubt on our understanding of nature, technology, and mystery. Numbers began to go awry on the evening of September 7th. Analysts, some in Tokyo, others in Arizona, watched as their graphs began to deviate from expectations. The Tri-I/Atlas, which was supposed to shine in increments of magnitude each week, instead increased its brightness by just 1.6 tenths in less than 72 hours. The first raw data, timestamped and uploaded by enthusiasts like Robert Machaut and Kei Yoshimoto, became available to the public. 10.4 at 2300 Coordinated Universal Time, then 8.8 just before dawn. Such a surge is not just a note, it is a signal of alarm. For several hours, the mailing list of comet observers and the Forum of Cloudy Nights filled with new data, each new point rising above the predicted curve. The usual slow growth transformed into a vertical wall. A jump of 1.6 meant the comet suddenly reflected 4 times more light than models allowed. Imagine that the dimmer is suddenly turned up to maximum in the middle of the night. Some claimed it was a release, a pocket of carbon dioxide bursting through the crust. Others whispered about artifacts of tools, aperture effects, the risk of seeing too much coma and mistaking it for a real flare. But the data kept coming in, each new entry questioning the old rules. This story, over several thrilling hours, belonged to amateur advisors. Their raw graphs, displayed in real time, became the pulse of global sky observation. No one knew what the next data point would bring, but everyone understood the stakes. When the light curve breaks, the cosmos tells you something you cannot yet name. The numbers are astonishing. By mid-September, Tri-I/Atlas, with a core no wider than 3 kilometers, possibly even less, was producing carbon dioxide at a rate of 129 kilograms per second. For comparison, this is a small truck of frozen gas, evaporating every minute from a body smaller than most city parks. The clearest images from Hubble captured a solid core about 2.8 kilometers in diameter, while the coma, a diffuse shell of gas and dust, expanded to over 700,000 kilometers in diameter. This is almost twice the distance from the Earth to the Moon, all traced back to a single, cold object. It's not just about size, chemistry behaves oddly too. Most comets in our solar system awaken gradually as sunlight penetrates their icy reserves, causing the water to evaporate. However, in this case, water plays a secondary role. The spectrum obtained with the James Webb Telescope on August 6th showed a carbon dioxide to water ratio of 8:1. This is not just unusual, it goes beyond the norms. At such distances, comets in the solar system usually show more water than carbon dioxide, often by 10 times or more. However, data about Comet 31/Atlas contradicts this pattern. Carbon dioxide predominates, while water lags significantly behind, and carbon monoxide is in third place. The JWST team, led by spectroscopist Dr. Alicia Franci, noted an anomaly in the early data. The models of her group predicted a slow increase in activity as the comet approached the sun, but the reality was entirely different. It was a runaway greenhouse. Carbon dioxide was released beyond the point where water was supposed to start appearing. As Dr. Franci expressed, we are observing a comet moving on completely different fuel. These observations have not only chemical significance. High-quality images from ground observatories and orbital telescopes show a comet surrounded by dusty plasma filaments, thread-like structures extending for tens of thousands of kilometers, curving and changing over a few hours. These are not the broad, uniform clouds we are used to seeing with ordinary comets. Rather, they hint at unbalanced processes, possibly even organized eruptions, as if the comet's core is pierced by jets or holes that expel gas and dust into space in powerful streams. And all of this comes from a core so small that its surface can hardly explain the observed gas activity. Physics requires at least 8% active surface to match the measured water production, while the level of carbon dioxide suggests even more aggressive emissions. Particle uplift models suggest that carbon dioxide eruptions lift small ice particles into the coma, where they sublimate away from the nucleus, feeding the comet's tail. This is a mechanism rarely observed on such a scale. The scale of the discrepancy is hard to overestimate. A stone the size of a city surrounded by an atmosphere that surpasses the sizes of planets. A gas emission that exceeds models by orders of magnitude, chemistry that looks like a recipe from another solar system. For now, the numbers themselves serve as a warning. Something in 31/Atlas rewrites the rules of comet physics, expelling 1 kilogram of carbon dioxide at a time. The color theory should not trouble astronomers, but by September 16th, the data on the spectrum of 31/Atlas forced a new interpretation. A sharp peak at 518 nanometers, right in the center of the green spectrum, cut through the noise, becoming noticeable sooner than anyone expected. Photometric data from the Gemini South Observatory first noted this rise. The image processing done by Catalina Hernandez that week marked each frame with a star. Her personal note to colleagues read, "The green envelope pierced the dawn sky like a chemical flare, unexpectedly for such a heliocentric distance. The green color left no doubt." Observers on 3 continents reported the same ominous light, often describing it as unnatural, almost electric. For those familiar with comet chemistry, this glow of C2, diatomic carbon, was produced by solar ultraviolet radiation. Comets usually show their green color within the inner solar system when sunlight breaks down organic molecules. Here, however, the effect appeared weeks ahead of schedule, and with a force that contradicted all known patterns. Hernandez's team measured the intensity of the emission lines and found that it rivaled the brightest comets ever recorded, even though Atlas was still far from the solar blaze. The technical explanation on paper is extremely simple. Fluorescent C2 is a byproduct of carbon materials released and activated as the comet heats up. However, it is not easy to explain why this happened now. Models based on decades of comet observations predict a gradual increase. Lines C2 should rise as the core crosses certain temperature thresholds. Atlas ignored the scenario. Spectrographs from Chile, Poland, and Hawaii all showed the same early increase. The green line cut through the background noise with such confidence that it left no room for doubt. Hernandez insisted on caution, spreading raw and processed images nearby, highlighting the risk of digital artifacts appearing. "We do not chase ghosts," she wrote, "but this is a regime where ghosts can look real." Nevertheless, the consensus grew. The green color turned out to be internal, not an optical illusion. The coma of the comet, now enlarged to a planetary scale, bore a spectral mark that distinguished it from all other interstellar visitors. Some speculated about a super-dense release of carbon chains. Others spoke of exotic chemistry inherited from the distant birthplace of the object. Each hypothesis added a layer to the mystery, but no one could explain why the green color appeared so early and why it burned so brightly. The effect was hypnotic. For several nights in mid-September, the sky offered a spectacle that seemed to defy both distance and expectations. The numbers told a story of energy and chaos, molecules torn apart and rejoined in the cold vacuum between the stars. But behind every analysis remained the question, what object bears an emerald halo ahead of time? And what else does it hide in its light? A burst of light, sharp and directed towards the sun, shattered the comet's shell shortly after September 9th. It was not an ordinary tail, but an anti-tail, a needle of dust seemingly pointing back to the sun, defying the rule that comet tails always point away from the solar wind. The geometry of this illusion is rare. The body of 3I/Atlas moves in a retrograde orbit, almost 175 degrees from the ecliptic, and the line of sight from Earth just intersects the dust plane almost at a right angle. For several nights, the comet's dust disk and the observation point aligned so perfectly that particles, separated months ago and now far behind, seemed to project forward towards the sun due to the play of perspective. This fleeting alignment transforms comet dust into a bright spike visible in long exposures from Poland to Chile. But the anti-tail is just the beginning of the puzzle. The polarimetry team from the University of Warsaw, led by Dr. Marek Nowak, conducted a study at a phase angle of only 7 degrees. The result was a minimal negative polarization of -2.7%. In the world of comet science, this is a warning signal. Most comets fluctuate around -1 or -2% at such angles, which is a sign of porous, irregular dust grains reflecting sunlight back to its source. Here, the significance is deeper and stronger than any recent comet, including the infamous comet sighting spring. The figures suggest not just dust, but a structure of dust. The particles are organized, possibly aligned in threads or layers, dense enough to polarize light much more than usual. What could create such order? Chemistry gives a hint. The Atlas coma is filled with carbon dioxide, a volatile substance capable of ejecting both powerful jets and small submicron particles into space. If the exhaust is directed through cracks, vents, or even electrostatic forces in a coma, dust can be gathered into coherent streams, each acting as a tiny polarizing filter. Data from the Warsaw Group, compared with amateur images from the same week, showed that the brightness and polarization of the anti-tail peaked simultaneously, hinting at a common origin. The phase angle matters. At 7 degrees, sunlight almost directly touches the dust, maximizing the backscattering effect. Negative polarization at this angle is a distinctive feature of highly porous aggregates formed in the cold and darkness of interstellar space. But the extremity of the measurement, -2.7%, takes the result into uncharted territory. No known comet of the solar system has shown such a deep minimum combined with an organized dust spike. At this moment, the anti-tail remains a silent cipher. This visible evidence shows that the dust around the Tri in the cosmic atlas is not a random cloud but something more organized and purposeful. Whether this order is the result of natural comet physics or a sign of something artificial remains an open question. Each new dimension points to a structure that is both beautiful and unsettling, a cosmic geometry that defies simple explanation. October 3rd, 2025 is circled in red in every mission plan. On this day, 3, and the cosmic atlas will fly past Mars at a distance of 0.19 astronomical units, about 28 million kilometers. In a season already filled with encounters with comets and asteroids, this is the only interstellar visitor within reach of the planet, a rare and fleeting opportunity. Mars orbiters, such as HiRISE on Mars, Reconnaissance Orbiter, KSI on ExoMars Trace Gas Orbiter, GRSC on Mars Express, face a chessboard of solutions. Internal emails, later quoted in press releases by the European Space Agency, describe a division of opinions. Scientific teams lobby for every possible opportunity, while operational teams weigh the risks of redirecting spacecraft on short notice. The ephemerides of the object are updated almost daily, leaving little room for error. Each orbital device has its limitations: angles of solar panels, data throughput, safety thresholds of instruments. The window for capturing images is measured in hours, not days. In the sky, chaos reigns. At the end of September, the comet 14P/Stereo swiftly passes perihelion. R2 Swan draws attention with its close approaches to Earth. A6 Lemon moves towards a solar convergence in November, while a wave of small asteroids fills the inner solar system, creating a sort of observational triage. Mission directors must choose: focus precious resources on a comet that rewrites the rules of the game, or stick to planned campaigns and risk missing a once-in-a-generation event. Pressure is building behind the scenes. A cluster of objects in the autumn sky heightens the urgency. Each candidate for observation is evaluated against the uniqueness of the 30I/Atlas, its interstellar origin, the prevalence of carbon dioxide in the coma, and a history that defies predictions. Schedules are rewritten. The shooting protocols, usually recorded months before the event, are torn apart and reviewed overnight. The operational pressure is palpable. Every change carries the risk of data loss, or, worse, a breach of instrument security. But the scientific interest is irresistible. No orbital spacecraft of Mars has ever recorded an interstellar comet so close to the planet. If the data is obtained, it could answer questions about the structure of dust, gas emissions, and the fundamental physics of objects coming from beyond the solar system. As October 3rd approaches, the feeling of a unique, irreplaceable chance intensifies. The sky is occupied, but for several hours, all gazes, both automatic and human, are focused on a single object. The result will not only fill a gap in a rich season of discoveries, but will also set the tone for how planetary science will respond when space opens a new chaotic chapter. Each anomaly requires a benchmark. For Comet 30 I/Atlas, this foundation comes from two interstellar predecessors. The first was Oumuamua in 2017, and the second was Borisov in 2019. Both rewrote chapters in planetary science, but they did so in remarkably different ways. Oumuamua appeared as a mystery, without a coma, without a tail, a light curve that changed with rotation but never emitted gas. Its trajectory through the solar system slightly deviated from the path dictated by gravity, subtly, persistently, and still inexplicably. Borisov, on the contrary, became a classic interstellar comet. Its gas and dust followed the rules, water and carbon dioxide caused activity, and the brightness curve matched models created for solar system objects. The numbers made sense. The physics was justified. Scientists, fearing an excessive reaction to exceptional cases, based their expectations for the 31st Atlas on these precedents. Data streams were processed by algorithms refined on the smooth ascent of Borisov and the persistent silence of Oumuamua. It was expected that the light curve would increase with the growing heliocentric distance, the coma would expand according to solar heating, and the ejections of material would create a familiar, predictable trajectory. Data sets on acceleration, collected by both ground and space telescopes, were ready to capture any deviations from gravitational motion, as seen with the curious drift of Oumuamua and the classic story of Borisov. The first weeks of observations matched predictions. Early photometric measurements showed a smooth increase fitting within comet models. Acceleration checks conducted by teams from the Jet Propulsion Laboratory, European Space Agency, and Harvard found no signs of non-gravitational push. The comet precisely followed its hyperbolic trajectory, its orbital solutions requiring no further adjustments. For a moment, it seemed that 31 slashes of the Atlas were a repetition of Borisov. An outsider, yes, but one that adhered to the rules. But then September came. A sharp jump in brightness, a swift coma, a spectrum rich in carbon dioxide, each new data point expanded the baseline. Scientists from the Small Planet Center and the Near-Earth Object Coordination Center meticulously examined acceleration logs, searching for any hints of the Oumuamua effect, but found nothing. The trajectory, at least for now, remains gravitationally justified. The anomaly seems to lie not in the path, but in the physics, chemistry, structure, and light, rather than in movement. The baseline, once a source of comfort, now frames a mystery. The data points not to a comet in flight, but to one whose internal processes are unlike anything ever measured in this field. In the absence of a non-gravitational smoking gun, attention turned to the chemistry of the object and the dust, where true anomalies and possibly real answers might be hidden. Speculation thrives where data is scarce. There is an opinion that the 31/Atlas could be something more than just a comet, a disguised scout, a technological artifact, or the first intentional visitor from another star. The arguments are based on three pillars. Firstly, the comet's coma, rich in carbon dioxide rather than water, suggests the use of an engine powered by unfamiliar fuel. Carbon dioxide, they claim, is not just a volatile substance. In the right configuration, it can serve as fuel. The physics here is not science fiction. Direct sunlight heating can activate jets of carbon dioxide, and in principle, a structure designed to collect and expel this gas could maneuver, or at least explain its brightness. Secondly, polarization. The measurement of the Warsaw team, which recorded -2.7% at a phase angle of 7 degrees, is the deepest minimum recorded for any comet in recent times. Some podcasters call it a sign, evidence of organized dust or artificial fibers. Scientists disagree, pointing to laboratory analogs. High porosity, fractal particles can cause similar effects, especially if they are charged and aligned by electrostatic forces in a carbon dioxide-rich coma. Science is tangled, but speculations appear neat. The order that chaos must reign, geometry whispering intentions. The third is the absence of data. The missing images of September and the silence of major observatories fueled numerous theories. Is this gap a mere artifact of solar elongation and scheduling, or evidence of controlled information? Influence is depicted as a pattern, a curtain falling at the moment when the object becomes most interesting. Meanwhile, scientists refer to the same limitations that cast shadows over each comet encounter: safe boundaries, delays in data processing, and the relentless geometry of the inner solar system. The Fermi paradox looms on the horizon. If the universe is full of life, why not disguise oneself among a swarm of natural debris? Why not embed a probe in the statistical noise of comets and asteroids? The engineering scenario looks enticing. Carbon dioxide as camouflage and fuel, polarization as a coded signal, and the absence of data as a deliberate pause. But each of these versions hovers on the brink of plausibility, forever ahead of the evidence. At this moment, the data only confirms what is visible. A comet breaking the rules, but not the laws of physics. The rest is a mirror reflecting our own quest for meaning in the silence between signals. Hubble telescope images from July remain available, and the spectra from the James Webb Telescope on August 6th were processed without delays. However, when the brightness of the comet and its behavior reached a new level, the rhythm of public releases weakened. The official reports for September lack fresh images from Hubble or James Webb. The usual public schedule of the Gemini Observatory does not show reserved slots for Comet 3 and A during the critical window when the light curve deviated from the scenario. The angular distance of the comet from the Sun, once a comfortable 45 degrees at the end of August, drops to 30 by the month's end. For Hubble and James Webb, these figures are hard limits. The risk to optics and electronics is unacceptable. Even ground-based telescopes, with their own horizons and twilight limitations, face closing windows as the comet moves towards the Sun in the pre-dawn sky. Amateur networks continue to publish reports and photometry, but high-resolution data from flagship observatories is absent from public records. The press services, so active in July and August, do not provide new recommendations. The risk is not in a conspiracy, but in a blind spot. An object rewriting the rules of comet physics at the moment when the world's best eyes are forced to look away. For those following this story, the September drought serves as a reminder. Sometimes the most interesting chapters in the universe unfold behind the curtain of routine, politics, and geometry. Every major celestial event draws its circle of risk, but the 3/Atlas forced scenario modelers to spend sleepless nights making uncertain calculations. The data deficit in September is not just an inconvenience. This is a window where the most unpredictable behaviors of a comet can unfold, remaining unnoticed. For those who spend their careers assessing the unlikely, the season of thought experiments has arrived. What will happen if the core fragments, remaining hidden behind the Sun? Can a sudden, invisible ejection, unseen from Earth, slightly shift an orbit enough to change a flyby past Mars or direct a cloud of fragments along new trajectories through the solar system? The mathematics of this question is both unsettling and alluring. An acceleration of 5 divisions at 10 kilometers per second, caused by a strong burst, could change the encounter with Mars from distant passes to a direct collision. This is not a forecast. It is an indicator of sensitivity, reflecting how little is needed for cosmic dice to land on another number. Microfragmentation, the slow peeling of icy shards, would manifest as a faint, periodic, bright glow. If only the best telescopes in the world were not occupied observing the blinding light. No similar signal has been recorded yet, but the absence of evidence is not evidence of absence. The comet's return to visibility at the end of November, a few weeks before its closest approach to Earth at a distance of 1.18 astronomical units on December 19th, will provide the first opportunity to check for debris trails, fresh ejections, or unnoticed course changes. Society craves answers, but science waits. In closed channels and internal memorandums, the language remains cautious. A window of risk, monitoring signs of fragmentation, tracking micro-releases. The stakes here are epistemic, not existential. Loss in the blind spot is not safety, but the opportunity to witness a rare interstellar object that rewrites the rules. 3 pillars still stand. A curve of light that defied all predictions, an atmosphere with high carbon dioxide content, and a level of dust polarization that doesn't fit any models. Until the curtain is lifted, scriptwriters can only launch their simulations, knowing that the next act depends on what the universe decides to reveal. On September 14th, 2025, the Small Planet Center recorded a brightness spike of Comet 3/Atlas at plus 1.6, triggering a global reaction. Spectroscopy soon revealed that a coma dominated by carbon dioxide had formed around a core less than 2.8 kilometers in size with a width of over 700,000 kilometers. Unusual data on polarization reaching -2.7% at a phase angle of 7 degrees still lacks explanation in modern comet models. Despite public images from space telescopes HST, JWST, and Gemini until the end of August, data for September became scarce, with no official explanations, only closed data and observation geometry. No non-gravitational acceleration or radio signals were confirmed. When 3/Atlas passed by Mars at a distance of 0.19 astronomical units on October 3rd, most of its perihelion was hidden behind the Sun. Do his anomalies reflect rare natural physics or unknown sources? So far, everything points to a real gap in our understanding. With the emergence of new data after the conjunction, answers, if they come, will arise from what is visible rather than what is assumed.